I've been wanting to do a derivation of Taylor series expansion for a little while. So I went out to YouTube and saw that this guy had made a video to kind of review it. Basically, we imagine some kind of arbitrary function. And it's not entirely arbitrary. It has to be a continuous function. And it has to have derivatives at all the points on the function. It has to be infinitely differentiable, which means, for instance, if this here is a vertical line, that might break the requirements, because, well, that would make it non-continuous, right? Because if it was a vertical line there, it would go over stop, and then it would continue down here, and it would be a discontinuity in the function. Anyway, I'm going to follow a couple of the steps that this guy made. Physics helps, so especially this one right here. This is kind of a definition of the secant line of a function. The slope of f is equal to the change in f divided by the change in x. So for instance, if we imagine this section right here, this slope is, this is delta f, this is delta x, and f prime is equal to delta f over delta x, and we can solve this thing by multiplying both sides by x minus a. F prime of x equals f of x minus f of a, and then add f of a to both sides. We'll have x minus a times f prime of x equals, or plus f of a equals f of x. Let's just make note that there's also something called the Maclaurin Expansion, and it's the same as the Taylor series expansion, except a equals 0. So this would become x times f prime of x plus f of 0 equals f of x, which is more familiarly known as y equals mx plus b, or y equals mx plus b. That's the standard form equation, or the slope-intercept form of the equation for a line. So if you use that equation and say this was your 0 point, then it would be accurate to about from there to there, but it would be inaccurate everywhere else. Now that is assuming the shape of a line. Let's say we want to use instead, imagine the shape of a parabola. So from that point we might make an approximation that it looks like that. I will make a much more accurate representation of the shape of the curve in that region, although it would still be inaccurate out as you get further away from that point. So I gather to make that assumption, Taylor went on to make an assumption about the second derivative of the function, which I think is sometimes called the curvature of the function. Anyway, the second derivative is equal to the change in the slope over the distance. So I'm going to take that function, multiply by both sides by x minus a, and then add the f prime of a to both sides. Now what does he do from there? He integrates f prime and then finds a constant of integration. Whoops. So let's see if I can't muddle through this. If this is just telling us how to get f of x from f prime of x by taking the integral of f prime of x dx minus a. So I think you would plug in limits of integrations from 0 to delta x if you wanted to think of it as a definite integral. and then it's a matter of integrating this thing. This is just a constant, so we would integrate that with the dx minus a, and when you multiply that by x minus a, it becomes x minus a. Then you want to integrate that, which becomes 1/2 x minus a squared over 2, or well, just x minus a squared over 2. And this f double prime of a is also a constant. So this is the curiosity. I have this point right here. I know the first derivative of that point and the second derivative of that point, and that basically gives me a nice parabola. It might not accurately represent that whole curve, but it'll represent a section in there from the low point to the high point. And all I need to know is the first and second derivative at that point there. Now this constant up here is just going to be f of a, which he derives with some, probably a little bit more clarity than I figured out by plugging in x minus a into f of x. And it comes up right there. Now we can start to see a pattern developing. If we start with that, we would have the first, or the non-derivative, f of a divided by 0 factorial times x to the 0. That's just 1 over 1, plus f of f prime of a times x to the first over 1 factorial, plus f double prime of a times x squared over 2 factorial, plus f triple prime of a times x cubed over 3 factorial. And you can, by continuing on with the process that we've started to develop here, you can keep this pattern going, and in summation notation it's just f of x equals f, the nth derivative, let's make it a sum from n equals 0 to infinity of the nth derivative of a times x minus a to the nth over n factorial, and it keeps going for infinity. Let me run through my 3 favorite examples: e to the x, sine x, and cosine of x. If you apply the Maclaurin series function expansion to each of these, e to the x is going to be 1 plus, I believe, x plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc. Sine x is going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And cosine x is going to be, and I should point out, this has to be in radians if you want to use this formula. Cosine x turns out to be 1 minus, can't get a minus sign out of that. Okay, minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Okay, I apologize. This is hyperbolic sine, and this is hyperbolic cosine. The sine and cosine are similar, except, for instance, sine of x is ix. Wait, this will be I sine x equals ix minus ix cubed over 3 factorial plus ix to the 5th over 5 factorial, if I remember correctly, where I is the square root of -1. Well, now I'm thinking I botched this completely. The hyperbolic sine is going to be all positive numbers. It's when you apply that I, these things start to alternate. These are plus, plus, plus all the way through 2, except when you have I squared, it becomes negative. When you have I to the 4th, it becomes positive. I to the 6th becomes negative, etc. In any case, if you do all this right instead of wrong, which the way I tend to do things, you can derive things like the hyperbolic cosine of x is e to the x plus e to the negative x over 2. Cosine x is e to the ix minus e to the negative ix over 2. Actually, I believe that one should be positive. This one should be negative. E to the ix minus e to the negative ix over 2I is sine x. If you can imagine a plane where the real numbers go off this way and the imaginary numbers go off this way, you can kind of imagine an angle theta here. Imagine this point being e to the I theta equals the real part plus I times the imaginary part. How could you extract the real part from there? So, for instance, imagine extending that line down that way. You can see this length here is, is r sine theta. Oh, well, r is just going to be 1, so that's sine theta right there. And this vector here is e to the I theta. This vector here is e to the negative I theta going that way. Well, the angle is negative theta, and so if you add those together, e to the I theta plus e to the negative I theta, and divide by 2, you get sine theta. On the other hand, if you subtract this e to the negative I theta, it goes this way. E to the negative I theta, and if you take e to the I theta minus e to the negative I theta, you get 2 times the imaginary part of it. So, which would be, well, that would be sine theta. Anyway, this should have been cosine theta. Anyway, maybe I'll remake this video, or when I have time to do the math correctly, or maybe I'll just see if it uploads the way it is.